All right, so in this talk, I will present some techniques. I should speak here. I'll present some techniques that we introduced to analyze countermeasures against cache attacks. So yeah, I will start the talk by introducing. Well, I'll use this. I'll start the talk by. Sorry, technical difficulties. All right, now I can change slides. So I will tell you what are cache attacks. Right? So the CPU cache is a small, fast memory that our CPU uses in order to get faster access to data from the main memory. So using the CPU cache vastly increases the speed of our computations. However, attackers may exploit timing differences due to the use of the CPU cache to break crypto implementations. And I'll give you a couple of examples. So first, we have the square and multiply algorithm for modular exponentiation. So what we do there is we implement, so we compute a base to a power e modulo n. And in crypto systems such as RSA, Helga-Mao, our exponent there is going to be our secret key. So what's happening here is that we go from left to right over the bits of our key. And if we have a bit which is 1, then we perform a multiplication. And it involves a high number of cache accesses. And these are both instruction and data cache accesses. Right. So if an attacker can detect these, then bit by bit he can recover the whole key. And such fine-grained attacks have been recently demonstrated, and they are able to recover essentially the whole RSA key from only making observations into one decryption round. And they have been also possible between co-located virtual machines. A different implementation for modular exponentiation does the following. It splits the exponent into windows, in this case of 4-bit. And then the loop here goes from left to right over the windows of the key. And what happens inside is, well, we do not have such secret-dependent branching as in the previous slide. However, we have some secret-dependent data accesses. So we are accessing some pre-computed value depending on some bits of our key. And so similar attacks were able to break this implementation as well. Now, what can we do to protect our code? So usually, a countermeasure that would be usually proposed by the scientific community is the so-called constant time coding practices. So these include, for example, avoiding secret-dependent branches and avoiding secret-dependent data accesses. The first practice is also known in the literature as the program counter security model. And such constant time code has been heavily deployed in Dan Bernstein's NaCl or SALT library. In practice, some more permissive approaches have seen a very wide deployment. I'll give you a couple of examples. So if we are using pre-computed values, such as these P2 and P3 I'm showing, an attack would usually then detect that, for example, only blocks of memory belonging to P2 are loaded into cache, into the so-called cache line. So to counter this, OpenSSL stores pre-computed values, so the same values, in some special layout, which then should ensure that no matter which out of the pre-computed values we are accessing, we will have the same sequence of cache line accesses. Another example for a permissive approach can be found in libgcrypt in their implementation of square and multiply. So over there, they have removed most of the key-dependent branching, but they still have this small key-dependent branch here. And if this branch is small enough that it entirely fits into a single cache line, then no matter if we take the branch or not, the code is going to be loaded into cache. All right, so looking into such permissive approaches. So what can go wrong here? Well, this code is so highly dependent on some well, pretty brittle details, such as the compiler, such as the hardware architecture. So how can we be sure that they're doing what they're supposed to do? In our work, we develop techniques which allow us to rigorously analyze cache attack countermeasures, such as the ones from the previous slide. For this, we rely on a hierarchy of attacker models, which correspond to different notions of security with different permissiveness. We measure security by quantifying information leaks with respect to those attackers. And a highlight from our analysis is that we symbolically treat dynamic memory, while at the same time we provide bit-level precision to be able to reason about memory alignment. We use this in a case study where we perform binary analysis of different implementations of modular exponentiation, which can be found in libgcrypt and OpenSSL in the last several years. All right, I will start with our attacker hierarchy. So this was motivated by some recent classes of attacks that had been demonstrated. First, we have the last level cache attacks. There we have an attacker who can distinguish memory accesses, so who can distinguish access cache lines. Then we have the control channel attacks, and this is an attacker who can distinguish access memory pages. We also have the cache bleed attack. There, the attacker can distinguish access cache banks. So how do we model all these attackers? Well, we consider an attacker who can observe memory addresses at a certain granularity. So this attacker cannot observe offset within cache lines, memory pages, and cache banks. In modern architectures, and these offsets are determined by the least significant bits of addresses. So by this, we can directly define a whole hierarchy of attackers. The first three lines correspond to the three classes of attacks from the previous slide. So they are ordered by the number of, by the visible bits to the attacker, which are marked green. Here on the last line, we're considering a stronger attacker who can observe the whole addresses. And here we are talking about both instruction and data addresses. So security with respect to this attacker corresponds to some very strong notions of constant time security. Now, if we have such an attacker observing addresses, how much information will leak to this attacker? For this, we rely on a standard leakage definition, which just says the leakage is the number of possible observations this attacker can make. For readability, we also take the logarithm of this. I'll give you an example. So we have a pointer x, which contains some address value. And we have a high variable. This means it contains, for example, some secret bit. Right. And if this high variable is not 0, then we will add 64 to x. Now, how much information leaks to an attacker who can observe the final value of x? We have two possible values of x, so the leakage is going to be 1 bit. All right, so far so good. So now let's see what happens if our x is dynamically allocated. And if we additionally know that the output of our allocator does not depend on our secret data. So this is non-secret or low data. So without making further assumptions on our allocator, then in the end, any 32-bit, so in a 32-bit architecture, any 32-bit value is possible. Right? So then our leakage is going to be 32-bit. So this is pretty high. And there, so in previous work, there has been little work on precise quantification in the presence of low data. So to get more precision, we do the following. We handle low data symbolically. So we assign a symbol to the output of our allocator, and we redefine leakage by taking the maximum of the possible observations for all possible instantiation of our symbol. So with this, we obtain x being either s or s plus 64, and their leakage is going to be 1 bit. So this is giving us a way to have more precision in the presence of low data. And so with this, I can go to a concrete countermeasure. So this is the ScatterGather countermeasure from OpenSSL, which I also briefly showed in the beginning. So there we are storing pre-computed values in this special layout. All right, so this layout is partially ensured by memory alignment that is going on here, which is done by the third line that we have here. So what's happening is we perform some bitwise AND with a constant, and this constant clears the least significant bits of the address. And then we add 64 in order to stay within the allocated region. Now, this line is familiar from the previous slide. So here we do not know the addresses, and we'll have to deal with this symbolically. Now, to reason about the next line, then we need to do some more precise bit level reasoning. In order to do this, we introduce a new construct, which we call masked symbols. So it allows us to capture values which consist of some symbolic part and some known part. So we know some of the bits. And with masked symbols, we can do arithmetic operations, such as, for example, if we do a bitwise AND between a symbol and a constant, which is exactly this constant, then we can learn that the least significant bits are zeros and that the most significant bits have not been changed. We can do also other things such as adding constants to the known bits. Now, with this, we can reason about leakage from aligned memory. So, all right. So, for this, we consider the case where we're accessing the first byte out of one of our pre-computed values, and we have here 8 pre-computed values. And so our analysis will tell us that the possible observations are going to be those 8 different masked symbols. So you see that they have different least significant bits and the same most significant bits. And so we obtain here 3 bits of leakage. However, with respect to our cache line attacker, which corresponds to last level cache attacks, our possible observations are going to collapse into only one observation because we're clearing here the least significant bit. And here we actually obtain a 0-bit leakage, or we prove that there is no leakage. All right, so this gives the intuition behind leakage quantification in aligned memory. A little bit more formally, we introduced the masked symbol abstract domain, which relies on a set of masked symbols. This domain supports arithmetic operations such as AND or addition subtraction. To get bit level precision, we rely on some basic arithmetic properties, such as, for example, for logic addition, we have the neutral element 1, the absorbing element 0. When we cannot be precise, we over-approximate by introducing fresh symbols. All right, and so this gives us a way to give a leakage bound by simply taking the cardinality of this set after applying a projection which is dependent on which attacker model we are considering. And we obtain the following result, which tells us that for all such attacker projections, our leakage bound is going to soundly over-approximate the actual leakage for all possible instantiations of our symbols. All right, so far I have considered only one memory access. So to be able to represent multiple accesses, we introduced the trace abstract domain. And it is essentially a data structure that allows us to compactly represent sequences of accesses in the form of a directed acyclic graph. So in each node of the graph, we have an element from our masked symbol domain. And the idea here is that the graph is going to over-approximate the paths in the execution, and the masked symbols are going to over-approximate the accesses at each point of the computation. All right, so the remaining elements that we need to perform our analysis are x86 disassembly, control flow reconstruction, and fixed point computation. So for this, we rely on the infrastructure of the cache audit abstract interpreter. It's an open source tool that we had previously been also working on. And so our tool passed the evaluation, and the source code is available online. Now, using our tool, we performed a case study where we analyzed different implementations of modular exponentiation. Those can be found in different releases of libgcrypt and OpenSSL. So essentially what we did is we compiled the different versions, and then we analyzed parts of the code which correspond to secret-dependent control flow or to secret-dependent accesses to pre-computed values. So here we're both looking into data and control flow leaks. I will first talk about data leaks. And so for this, we analyze data cache accesses. Right, and so these are our results. I will just focus on the right-hand side. So here in the first column, we have an implementation which does not deploy any countermeasure. Our tool reports it as leaky. And on the right-hand side are the two last fixes from libgcrypt and OpenSSL. And our analysis shows that over there, the problem has been solved. What's more interesting is what happens with ScatterGather. So our initial results were this, that for the strong address-based attacker, we report a high number of leaked bits. However, for the cache line attacker, our tool reports that the problem is solved and there is no leakage. Now, shortly after we had our first results, a new attack was demonstrated. It was called cache bleed, and it exploits cache bank usage in some recent CPUs, and it was able to break ScatterGather. So in the week after this was disclosed, we did two things. We repeated the analysis with respect to the new attacker, which confirms the leak, and we analyzed the patch that was immediately released by OpenSSL, which shows that for the considered attackers, the problem has been solved. All right, now let's look into control flow leaks. For this, we are looking into instruction cache accesses. All right, so here I'm focusing on examples where we have some secret-dependent branches. You see here in most of the cases, our analysis reports one bit of leak, with one exception. Now, let's see what's going on there. So in the last line, I'm considering a slightly weaker version of this attacker who cannot observe consecutive cache hits. If we access twice cache line A, then 3 times cache line B, the attacker will only know that we were first in A, then in B. And the 0-bit leak here corresponds to a key-dependent branch that entirely fits into a single cache line. Now, it's interesting to note that we have a small branch that in this implementation as well. However, it is reported as a 1-bit leak. And this is the code that corresponds to this key-dependent branch. So we have here highlighted with blue is the if condition and with red is the else condition, or vice versa, I'm not sure. The important thing is that what's happening here is that if an attacker observes that we're first in the first line, then in the fourth line, then again in the first line, then he'll know that we accessed the blue branch. Otherwise, he'll know that we accessed the red branch. Now, it's interesting to know that if we take the same C code and we compile it with GCC with optimization level 1 instead of 2, then we have the following result. And here, in both cases, the attacker will first observe accesses to the first line, then to the second line. And for this, our tool reports a 0-bit leak. And now to wrap up, I presented techniques for analyzing countermeasures against cache attacks. We rely on a hierarchy of attackers who can make observations with different granularity. And we quantify leakage for a code that contains the memory alignment in dynamic memory. We performed the first rigorous analysis of permissive countermeasures, and our experiments show examples where the countermeasures work and other examples where the countermeasures do not work. So thank you. Where am I looking?
So right now you're assuming that any address that comes from dynamic memory is deterministic. It exposes all of the addresses. What if you had a dynamic memory allocator that had guaranteed entropy, so that you really had very little information about where memory addresses were coming from? Would you be able to model that, and would that affect the analysis?
Wait. So if I understand, so we do not make any assumptions on the entropy of the dynamic memory.
Right now, yeah, I mean, I understand.
Yes.
The question though is, so when you're an attacker, you do these attacks, you launch them against something because it has this particular addresses. You can imagine a situation where everybody who allocates memory is getting memory that's individually randomized and it's separate.
Okay.
So you could quantify probabilistically what the likelihood of success would be, or the amount of each bit.
So they are in the.
I'm just wondering if you could model that sort of thing in your analysis.
So what you're saying that our dynamic memory is going to be then secret, like, or yes. Of course, yeah. I mean, but actually, well, our straightforward approach with like where we do not do symbolic stuff, then you just handle this data as if it was a secret. And then that's why I'm saying, okay, we're obtaining this imprecise bounds. But well, if this is our secret, then the bounds then there are going to be precise.
Hi. So,
Hi.
Nice talk. So following up on that question, so I think you are assuming that global variables and stack locations that they parallelize known locations, correct? So
Yes.
if you have a heap allocation, just say there's bit vector of unknown value, right? You know, some little, but for like the stack allocation or global variable, you know exactly what you assume the attacker knows exactly what the value is.
Yes.
Right? Okay. So then to make things worse, those attackers could potentially pilot could randomize those locations.
Of course. Yeah. Yes. Yeah, I mean, we haven't done this, but essentially you can try the same. I'm not really sure what the exact limitations would be. There. Yes, exactly. The only so yeah, the only thing is you should figure out how to do. So there you really have some control flow, which is where you don't know exactly where you're going. So I'm not really sure what the limitations there are going to be, but for certain things you can do this. Yes. Yeah.
So I understand that you take the max over low.
Sorry?
Max over low to get
yes.
Yeah, too high. And you consider repeated attack. Adaptive attack. Attack or repeatedly attack. You consider.
We don't consider repeated attacks. So, but So I'm not sure about adapt. So yeah, I mean, so one thing is if your leakage is going to like accumulate, right? So like right now our assumption is that, well, so essentially it could you can just add up the leakage for this, but for this we can take it offline. Yes.